Okay, I'm going to go through this AQA A-level chemistry paper, paper 2, organic and physical chemistry, and it's the June 18 paper. I'll just do half the paper to keep the video relatively short, and I'll carry on with the second half of the paper in another video. Okay, so the first question is about alkanes. Alkanes can be used as fuels. An equation for the combustion of heptane in excess oxygen. Okay, so we've got C7H16 react with oxygen. Complete combustion, you're only going to get carbon dioxide and water, no carbon monoxide. Balance for the carbons, I'm going to say, right, we need 7 CO2s. Balance for the, we're going to need 8 waters for the 16 hydrogens. That gives us 14 oxygens there, plus 8 here makes 22, so we need 11 in front of the O2. That's balanced. Okay, so this is asking about catalytic cracking, so not thermal cracking. Okay, high temperature. So we need a suitable catalyst. Well, the answer there is just zeolite, which is actually some kind of aluminium oxide, trade name for aluminium oxide, a zeolite catalyst. One other condition other than higher temperature, you need like moderate pressure, not high pressure. And now we want an equation. Okay, so for the cracking, so it says we start off with C16H34, and we're going to break that into the smaller molecules of heptane. So that's going to be C7H16. A cyclohexane, that's C6H12. Remember, cyclohexane, because it's cyclic, it's CnH2n, not +2. Okay, so it's going to be that. And if you add up, right, just to make that equation balance, we're going to, well, we've got 13 carbons on the right, 16 on the left, so we need 3 carbons, and out of the hydrogen, that's 6. So you get propene would be the other product there. All right, okay, alkanes can be used in free radical substitution reactions to produce halogenoalkanes. We want equations for the propagation step to produce in the reaction to form. So we start off with butane, C4H10, and we're going to substitute it to form 2-chloroputane. So it's going to be C4H9Cl. Okay, right. So anyway, the first step is we are going to get in the propagation, C4H10 reacts with the chlorine-free radical. Of course, that's being made by the initiation step. You split up a chlorine molecule. The chlorine-free radical is going to grab a hydrogen off that, and on position 2 will be, but we'll just write C4H9, and that will leave a free radical behind and make HCl gas. That's propagation 1. And the second propagation step, then, this is very reactive free radical. It will react with a chlorine, another chlorine molecule, to produce the product C4H9Cl and a chlorine free radical. So you can see that the chlorine free radical gets used up, but then it gets regenerated. So this could, it's like effectively like a catalyst. It could go around lots and lots of times. Okay, so now, right, so this is about chlorofluoro CFCs, and they're banned, says here, because they can deplete the ozone layer. Okay, so identify the radical produced by the CFC that's responsible for the depletion of the ozone layer. Right, now it is the carbon-chlorine bond which gets broken by UV light in the upper atmosphere to produce the chlorine-free radical. The CF bond is too strong, it won't be broken. Now, and with additive equations, explain how it can cause decomposition of the ozone. So we need 2 equations there. So we get chlorine-free radical reacts with O3, which is ozone, and that will give another free radical, the ClO. That's a free radical. If you draw a dot cross diagram, you see it has an unpaired electron, and you'll have oxygen gas. And then the chlorine-free radical, which is very reactive, of course, will react with another ozone molecule, creating 2 molecules of oxygen and regenerating the chlorine-free radical. So we've got, of our 4 marks here, we've got 3 marks, 1 for identifying the radical, 1 for each of those 2 equations, and the 4th mark, we've got to say that the chlorine free radical is regenerated in this reaction. It's effectively like a catalyst, and it can go on and catalyze the destruction of more ozone molecules. Okay. Right, so this is about organic synthesis. Halogenoalkanes are useful compounds, and the reaction pathway is shown below. Right, okay. Now, before we have a look at that, give the UPAC name for this compound here. Now, I strongly advise you to always draw those out in displayed formula or semi-displayed formula before you try and name it. I wouldn't try and name it by just looking at that. It's very easy to make a mistake. Now, we should number the carbons here. Now, the OH, that is the main functional group, so that should be on number 1. You can number it from that way around. So we've got 3 there. So we'd have to call that 2-methyl, methyl group on number 2, 3-bromo, propan 1 ol. And because the methyl can only go on number 2, you could actually get away with not putting that number 2 there, and that would be right. Okay, probably best, yeah, okay, so, yeah, okay, that would be best to leave it off because it's not entirely necessary. Okay, right, reaction 1, I've put this scheme, occurs via a nucleophilic substitution reaction. So you can see what we've done here is reaction 1. Let's just have a quick look at this reaction scheme, what's going on. Here, we swapped a bromine for an OH, and so that's going to be nucleophilic substitution. Here you can see if you count up the oxygens, well, you've got more oxygens and you have actually lost 2 hydrogens here as you go from there. So that is an oxidation reaction. And you have, obviously, you've got 2 you've got 2 alcohol groups and you've oxidized both of them. Okay, right, so right, let's have a look at that then. So reaction 1 occurs via a nucleophilic substitution mechanism. Explain whether halogenoalkane is attacked by the nucleophile in this reaction. Okay, so we've got here, we've got carbon with a bromine attached. 3 marks. So I think what you've got to say here is, first of all, say that the bromine is more electronegative. That will give you 1 mark. So that causes a partial charge on the carbon, partial positive on the carbon. Draw it as delta positive. And that means the lone pair on the nucleophile is negatively charged, is attracted to this carbon. There's your 3 marks there. Okay, right. So let's have a look at compound Y. It's not immediately apparent exactly what's going on there. So we have got up here, we have got, oh, sorry, we have got 3 carbons long. We've got a CH3 there, and we have got an OH now on both ends. So we've got 2 primary alcohols. Right. And if we just count up the number of oxygens there, so we've got 1, 2, 3, 4, 5, 6, 7. We've got 10. We've got, sorry, hydrogens. We've got 10 hydrogens. So we have actually lost here 4 hydrogens. Okay, and I think what's happened is, right, we have probably oxidized each end to an aldehyde. Okay, so I draw that. That's what's happened there. Okay. We obviously haven't oxidized it all the way to a carboxylic acid because we haven't got enough oxygens. We've only got 2 oxygens, but we formed an aldehyde on each end. Okay, that's what we've done. Right, now question 2.3, it says the infrared spectrum shows us an absorbance in that region. That is very characteristic of the carbonyl group. So we've definitely got carbonyls in it. Now, it does say draw the displayed formula. So the way I've drawn this, I wouldn't get any marks because with displayed formula, you've got to show every bond, and I haven't there. So I'd have to write my CH3 like this. Okay, so be careful of losing marks like that. Right, now compound Z, this was a mean question. It's got an empirical formula of C3H4NO. Now that's very misleading because look what's happened here. We've got 4 carbons there, so it looks like it's lost a carbon, but then gained some nitrogen. And you're thinking, what on earth kind of reaction would that be? But the trick question here is, it doesn't say molecular formula; it says empirical formula. I think the molecular formula of compound Y must actually be double that, C8H12. Sorry, not compound Y, compound Z. Sorry, must be actually be double this. So it's going to be C6H4H8. Sorry. N2O2. So you can see as we've gone from there to there, what have we done? Well, we've actually added on 2 nitrogens, 2 carbons, and 2 hydrogens. Now, if you think about whenever you're adding a carbon and a nitrogen, you're obviously adding a cyanide on here, aren't you? Okay, that's what's happened. Okay, so if you draw the structure of compound Z, well, what's happened is, let me think, if you know, so that's a cyanide, the cyanide ion will undergo nucleophilic addition. That's a nucleophile. It's going to attack that carbon there. Pi bond breaks, and of course this oxygen then picks up a hydrogen to form the OH, form a hydroxynitrile. So if we draw the structure of compound Z, we're going to get, right, so we've got this bit is unchanged. The carbonyl is turned into an OH. We've got a cyanide group stuck on there, or a nitrile, right? And we've got an H on there. Sorry, I've missed an H off there. Should be an H there. So we've got an H there, and the same on the other side. We've got OH. Right, that was a very sneaky question that a lot of people didn't realize the empirical formula. I would have marked this question and we got completely stuck on it, couldn't think what was going on. It's because it's empirical formula, not the molecular formula. So that is the compound. Now the reagent to carry that out, do you remember to add a cyanide to an aldehyde group or a ketone group? The reagent is potassium cyanide followed by hydrochloric acid. It's not just potassium cyanide. You won't get the mark for just saying potassium cyanide. Or you can say, instead of that, you can say HCN. But you can't just say KCN. Okay? The nucleophilic addition. Right. Okay, so here is a question here. Oxidation of propan-1-ol can form propanal and propanoic acid. Let's draw those out. And okay, so let's just draw them out. So propan-1-ol obviously is that. Propanal is the aldehyde group, and propanoic acid. It's like that. Okay. Right. And it's going to be about intermolecular forces, this question, because look, they give us the boiling points there. Right. So in the preparation of propanal, propan-1-ol is added dropwise to the oxidizing agent, and the aldehyde is separated from the reaction mixture by distillation. So you're going to have something like this. You've got a flask with a distillation bit set up on it. There's my condenser. But you must have some kind of sidearm here with a tap on it, which allows us to put in the propan-1-ol. Okay, thermometer there. Right. And we've got our propanol and the oxidizing agent in there. Explain with reference to intermolecular forces why distillation allows propanol to be separated from the other organic compounds in this reaction mixture. Well, propanol has got a much lower boiling point, okay, for 3 marks. So I think the reason we just have to say it's got a low boiling point, we'll get a mark for that. Why has it got such much lower boiling point? Well, look at here, the intermolecular forces. You've got a hydrogen there attached to an oxygen, so you can get H bonding here. You can get H bonding with carboxylic acid. You've got a hydrogen attached to an oxygen. That's going to make that very delta positive. But in propanol, you don't have a hydrogen attached to an oxygen, so no H bond. So the strongest forces you're going to get are dipole-dipole interactions. No H bonding. So, and H bonds are the strongest kind of intermolecular force. So the it's going to be weaker. It's going to be a lower boiling point. Sorry. Okay, so I think for the 3 marks, you've got to say low boiling point, mention the hydrogen bonding in propanol and in propanoic acid, and then say no hydrogen bonding in propanol. Right, 2 ways of maximizing the yield of propanol obtained by distillation of the reaction mixture. Well, the first one is reasonably obvious, and what you should do is, there's my thermometer there, is you should keep that less than 97 degrees C, because if you don't, you're going to get your reactant distilling over and it won't have a chance to react. That is the obvious one. The less obvious one, and you want to make sure that your this is quite volatile, 49 degrees C, so you're probably best collecting that in a cold water bath. Otherwise, you're going to lose some by evaporation for the second mark. So keep the temperature below 97 and collect it in an ice bath. Okay, this bit here, how would you carry out a simple test tube reaction to confirm that the propanol is not contaminated by any propanoic acid? So be careful here. It's not asking you to show there's propanol in it, and you might think, oh, well, it's an aldehyde, use Fehling's test. It's not asking that. It's asking to show there's no propanoic acid. So what you should do is you should add sodium carbonate or sodium hydrogen carbonate solid, and you should look for effervescence or fizzing. Okay. If there's any fizzing, it means you've got a carboxylic acid in there. No fizzing, you haven't. So you're looking for the absence of effervescence. And the main reason people got that question wrong, I think, is because they didn't read the question correctly, and they just jumped to it and said, "Oh, prove propanol is there with Tollens or Fehling's." Yeah. Okay. Number 5. Right. A mixture of isomeric alkenes is produced when pentan-2-ol is dehydrated in the presence of hot conc sulfuric acid. Pent-1-ene is one of the isomers produced. Name and outline the mechanism. Right, now when it's called dehydration is the mechanism. Right, and the sulfuric acid is a catalyst, so we need to get 1 mark for naming it. Let's do the mechanism now. So rather than draw the whole thing out, I'm going to draw just the last 2 carbons. That's all that matters. So you can draw the OH like that. Okay, so now the first step in the mechanism is we can draw H+. You don't have to draw it attached to the sulfuric acid. It's not necessary to do that. They don't want you to do that. So it's going to pick up an H+ from the sulfuric acid. So we draw a lone pair on the oxygen. That's going to go onto the hydrogen, and that's going to give us this intermediate. Let's rub that one out. We will get there. We'll get, sorry. So we protonate the oxygen. So the oxygen's now got a positive charge on it, and we're going to have that. Now the next step in the mechanism is this bond is going to break, and that pair of electrons are going to go there to form the pi bond, the double bond. That means this carbon here is going to be forming too many bonds. So, sorry, I'm drawing that arrow the wrong way around. That's not right. That that pair of electrons is going to go in this bond. Is going to go onto the oxygen. Okay, due to the positive charge on the oxygen. And that the pair of electrons in this bond, that's going to make the pi bond. So you're going to end up with a double bond there. You've got two hydrogens here, hydrogen there, and you of course released H2O. And this hydrogen here, well, this has come off as H+, so you've regenerated the H+. So you started off with H+, you get H+ back. So the role of H+ in that reaction is a catalyst. It doesn't ask you that, but so 3 marks you get for well, there's maybe 4 possible marks there. Depends how the mark scheme goes. You've got this curly arrow here, a mark there, that curly arrow, and there'll be a mark for having a positive on that oxygen there, the correct intermediate. Okay. 3.6. Okay, a pair of stereoisomers is also formed in the reaction in 3.5. Right, so let's see. What we've got here is we had pentantuol, yeah, pentantuol. So I'll just draw that out. With the oxygen, there's the OH. Now remember, in dehydration, you remove the OH and you remove a hydrogen from the carbon next door. Now, if you remove the red hydrogen, you're going to end up with pent-1-ene. But if you remove this blue hydrogen here, you're going to form a double bond here, and so you're going to end up with pent-2-ene. So you want to get some of that as well. So let's draw pent-2-ene. Right, so I'll draw that like that. So we end up with we've got CH3 and an H. We've got an H, and then we've got CH2. And we need to 1, 2, 3, 4, 1 more there. Okay. Now that isomer I've drawn, you can see we've got the 2 high priority groups. We've got no. Well, let's see. Explain how this kind of stereoisomerism arises. It's obviously due to the double bond, say that, and the fact that you can't, no rotation against a double bond for 1 more. And you have to name the less polar stereoisomer. Now the one I've drawn here, they've got the high priority groups. These are on the same side. Okay, so that would actually be the Z isomer. That is actually more polar because you've got all this negative charge on that side of the molecule. That's more polar than the E form. So if I draw the E form, I'll just swap it around. You've got a more even distribution of the electrons in the molecules there of the molecule. You haven't got it all on one side. You've got this electron heavy bit here, and you've got the electron heavy bit here. So they're not all on the one side of the molecule, so that will be less polar. So the name of the less polar isomer, that's the E isomer, is E pent-2-ene for the other mark. Right, now an equilibrium reaction one with a pretend chemical reaction with just A's and B's instead of proper chemicals. Okay, so what we got here, then we've got quite an awkward ratio to work out. Quite an awkward. There's quite a lot of 2s and 3s and stuff here. Okay, so we're going to have to construct one of these usual diagrams here, where we have 2a plus b goes to 3c and d, and I put down here start moles, used up moles, and final moles. Okay, now let's fill in what we can here. So the start moles of A, right, now they make it even more tricky here because they don't tell us. They say that we've got to work out the moles A is conc times volume. So we've got 0.16 over times multiplied by 20 over 1,000, and that is going to give us 6.4 times 10 to the 3 minus 3. Okay, so write that in there. So we had to do a bit of work even before we started there. That many moles of A. You've got 9.5 times 10 to the minus 3 of B. We've also got some C, so that makes it more. Quite often these don't usually have any products there. We have with the C, that's 2.8 times 10 to the minus 2. Actually, B, that's 10 to the minus 2 as well. Sorry, I can't read. 2.8 times 10 to the minus 2, and we've got no D. Right, the equilibrium mixture, it said when it's reacted, we've actually got 3.9 times 10 to the minus 3 moles of A. So how much of A has been used up? So we subtract 3.9 from this one here, and that is going to give us 2.5 times 10 to the minus 3. Okay, now we've used that much A. We've used up half the amount of B because it's 2A reacting with 1B. So the amount of B used up is 1.25 times 10 to the minus 3. And the amount of C formed, well, we're going to form 3 times this value. So that's going to be 3.75 times 10 to the minus 3. Okay, so what we've got to do then is, first of all, with B, we've got to subtract 1.25 from 9.5. So the amount of B left over is 8.25 times 10 to the minus 3. And the amount of C, we've got to add these two together. So it's a bit unusual, this question. And that gives us 0.03175. So calculate the amounts of B, C, and D in the mixture. Oh, we haven't done D. Now, to every time 1 mole of B reacts, you form 1 mole of D. So the amount of D is going to be 1.25 times 10 to the minus 3. Okay, so there's our answers there. There's the amount of B, the amount of C, and there's the amount of D. Right, so now move on. Is asking us for the equilibrium constant and its units. Okay, so let's do that. The equilibrium constant is going to be Kc is equal to concentration of C cubed times by the concentration of D divided by the concentration of A squared multiplied by the concentration of B. The units, well, we've got 4 concentration terms on the top. So that's going to be mole per decimeter cubed to the power of 4. And we've got 3 on the bottom. So that's just the same as having that 3 is going to cancel out on that 4. So the units are just going to be mole per decimeter cubed. Okay. So that's that bit done. All right. So we're going to need this expression for afterwards. So I might copy this actually. Right. So, right. As usual, in case you don't get that first bit right, they always start off again saying a different equilibrium mixture of these 4 compounds. Okay, so we're going to have to use that expression. I'll paste that there. At a different temperature contained this many moles of B, C, D in a total volume of 5 times 10 to the 2 centimeters squared, which of course that is equal to is equal to 500, which is equal to 0.5 dm cubed. So a little bit of messing about with units from them there, yeah, and standard form and so on. So 500 centimeters cubed, 0.5 dm cubed. Right, and they give you the value of Kc, and they want you to work out the concentration of A. So we basically got to put the numbers in there. So let's rearrange it for A first of all. So if you rearrange that, we're going to get the A concentration squared is going to be equal to C cubed D divided by Kc over B. And where people mostly go wrong in these questions is they confuse moles with concentrations. And of course, these square brackets here, they all mean concentrations. So we've got to do moles over volume every time. And the volume, of course, that is, we worked out that was equal to 0.5 of a dm cubed. So if you just put all those numbers in there, you would end up getting A squared is equal to 1.05 over 0.5 squared multiplied by 0.076 over 0.5 divided by Kc, which is 116, and divided by the concentration of B, which is 0.21 over moles over the volume, which is 0.5. Right, so if you work all that out on your calculator, you get that A concentration of A squared is equal to 0.16, sorry, is 0.0289. Take the square root of it, and you should get the answer is 0.1699. Now, you should really give this to the right appropriate number of significant figures, right? You should give it to some of the data you're only given to 2 sig figs. B there, you're only given to 2 significant figures, and D you're only given to 2 significant figures. So you should only really give your answer to the least accurate bit of data. So you should only give it to A is equal to 0.17, and the units mole per decimeter cubed. They only usually do that once per paper, where they're really, or once or twice per paper, where they're really keen on the significant figures, and they always tell you, they always kind of flag it up, saying give it to the appropriate number of significant figures. So I wouldn't worry about it. Most of the time, just give 3 significant figures, but do look out for questions when it says that, and they will knock a mark off for that, which is quite a lot to lose 1 mark out of 3 for doing all that working out. Okay. Right. Now, this question here, justify the statement that adding more water to the equilibrium will lower the amount of A in the mixture. Right. Now, the way I'm going to do that is I'm going to paste in that equation again. There is our equation for Kc. Right. And what we're going to say is, right, the concentration of each of these things is equal to the moles C divided by the volume. So that's the concentration of C. Right, so I'll do the concentration in black and that one in blue and in red. Okay, so what I'm going to do is going to substitute all those into that expression. So get rid of all the concentration terms and make them moles instead. And okay, so there we're going to get Kc is going to be equal to the moles of C over V all cubed. The moles of D, this lowercase means that it's the moles, not the concentration, over V. The moles of A over V, that's squared, and the moles of B over V. Let's multiply that out to get rid of those. Okay, so we multiply that out with that Kc is equal to C cubed over V cubed multiplied by D over V divided by A squared over V squared multiplied by B over V. Now, loads of these V's are going to cancel out. Okay, so I am going to get rid of the 3V terms on the bottom. So that means I'll go with them. So that means I've just got 1V there. So if I rewrite that, I get Kc is equal to C cubed, that's the moles of C, D, divided by A squared B multiplied by V, where V is the volume. Now the question, it says if you add more water, so that means what we're going to do to the volume, we are going to increase V. Okay, V is going to get bigger. Kc is going to stay the same. So that means that this fraction, to keep say the same, this, if V gets bigger, this has got to get smaller. Okay, so that means to keep, if V is getting bigger, this fraction is going to get smaller. So that means we have got to get less A. Actually, sorry, that V will go up on the top. I do beg your pardon. That V is going to go on the top. So if V gets bigger, this fraction has got to get smaller. So that means the amount of A has got to decrease. A must get smaller. So V bigger, A smaller. Okay, right. Let's move on to the next question. Actually, I think we'll leave that there because this video is getting quite long. So we'll move on to question 5 in the next video.